Whoops. Welcome back. In this section, we're going to be looking at the arteriolar radius, what affects it, since we've already talked about how radius affects blood pressure and flow. So first, I want to review the neurovascular effects on, so we're looking specifically at blood vessels here, not at the heart, but at blood vessels, we have sympathetic and parasympathetic as well as sympathetic cholinergic nerves. So most of our sympathetic nerves to blood vessels are going to be adrenergic. So they are going to use norepinephrine as the neurotransmitter through those alpha-1 and alpha-2 receptors, and that gives us vasoconstriction. But our parasympathetic nerves, as well as we have some cholinergic sympathetic nerves, they are all using acetylcholine as their neurotransmitter. And so they are going through muscarinic receptors, and the net result is going to be vasodilation. So let's look in more detail how acetylcholine causes this effect. And the way it causes it is through the most potent vasodilator in your body, the absolutely most potent substance we have, and that's called nitric oxide. Not to be confused with nitrous oxide, which is laughing gas, which makes you sound funny and is also used as an anesthetic agent. Okay, so getting back to nitric oxide. In the blood vessel wall is where we're talking. When acetylcholine as either a parasympathetic neurotransmitter or as a sympathetic cholinergic transmitter, when it binds to its receptor, that's going to couple two actions. The first being a G protein linked receptor being stimulated in the endothelial cells. And that gets coupled to relaxation of the smooth muscle cells. So notice the effect is not in the cell where the G protein is located. We are making two cells work together. So let's get it in a little bit more detail. This paler cell, this tan colored on your left, that is the blood vessel endothelial cell, that simple squamous endothelium. The taupe color on your right, that is the smooth muscle cell, which is deep to the endothelial cell. So we have acetylcholine receptors on the endothelial cell. And when acetylcholine binds to them, then there is a G protein, which does what G proteins always do. They get activated, and then it's going to work with a second messenger system. And in this case, we are back to the PIP2 giving us DAG and IP3. And once again, we are interested in IP3. So IP3 goes to the endoplasmic reticulum, causing the release of calcium ions, okay? And those calcium ions, in this case, activate something called calmodulin, okay? So in other words, we're not talking ryanodine receptors here, okay? The calcium is coming out, activating calmodulin. And what calmodulin does is it activates an enzyme known as nitric oxide synthetase, okay? Which means synthesis, we're going to be making nitric oxide. How do we make that? Well, we start with an amino acid. It's not important that you know that it's specifically arginine. And then we end up taking an N and O off of it, nitric oxide. So that nitric oxide then has an effect on the smooth muscle cell, not directly, but because it causes the formation of something known as cyclic GMP, not cyclic AMP, but cyclic GMP. And so the way this works is that nitric oxide activates the enzyme, which is used to take GTP and make cyclic AMP. And then cyclic AMP becomes another second messenger in this cell and activates a protein kinase. In this case, because it's not cyclic AMP, it's not protein kinase A, but because it's cyclic GMP, we call it protein kinase G. And then protein kinase G is what causes that smooth muscle to relax. And when the smooth muscles of the blood vessels relax because they are in a circular formation, that means the blood vessel diameter increases or the blood vessel vasodilates. So go ahead and stop it here if you need to kind of go through the details of this to understand it. So we're only adding a couple of things, okay? So I think you should get this, but if you don't, please make an appointment with either me or somebody else, you know, or your group study and go over this and ask questions or send them by email. So the net result is when acetylcholine, whether from parasympathetic or sympathetic cholinergic receptors binds, then what happens is through a couple of second messengers, we're going to have, well, through a second messenger, we're going to have nitric oxide released from the vascular endothelial cells, which then stimulates the formation of a second messenger in the smooth muscle cell, causing the vascular smooth muscle relaxation. Okay. So let's back away from those little details and kind of look at different categories of things that influence the radius of arterioles. So neural controls, I've just been talking about sympathetic neurons with that are adrenergic, and then parasympathetic and sympathetic neurons that are cholinergic. Hormonally, we understand that epinephrine and norepinephrine can be released and would have effects. And we also have effects with vasopressin, which we've learned about already. And other things, angiotensin 2 and HO natriuretic peptide, we haven't learned about them yet. We're going to learn about them when we talk the renal system, which means we're coming back to this one more time near the end of the semester. And then locally, we have effects that have to do with chemoreceptors, looking at oxygen content and CO2 content and pH, as well as other substances released during injury, as we've talked about before. As you can see, this is not just straightforward. Well, one thing causes this, you have to take a lot of things into account. And so I just want to remind you before we get into the next couple of sections that if you need to, pause it here and review the anatomy of the various types and sizes of blood vessels, because you'll need to have that as fresh memory in order to understand where we're going for the next few Zoom videos. So thank you once again for all your work in this class, and I'll see you shortly.